Today we're going to be talking about the relationship between inscribed angles and their subtended or intercepted arcs. This is also going to allow us to find the measures of the angles of inscribed polygons. First, we need to look at the definition of an inscribed angle. There's an example below. You can see it. The first most important thing is that the vertex must be on the circle and that each of the sides of the angle is a chord of the circle. In fact, that is the definition. It's an angle whose vertex is a point on the circle and whose sides are chords. The intercepted arc is the arc that you find in the interior of that angle. An inscribed polygon is a polygon whose sides are the chords of the circle and whose angles are the inscribed angles. If an angle is inscribed in a circle, this is our first theorem. If an angle is inscribed in a circle, its measure is half the measure of the intercepted arc. Or you could also say that the measure of the intercepted arc is twice the measure of the inscribed angle. We're not going to do a formal proof of this, but let's go ahead and take a look at why that happens. First, to do this, we're going to use some auxiliary lines. If I were to draw in the radii between the center and each point on the circle described by the inscribed angle, what I end up with are isosceles triangles. The reason these are isosceles is because the radii of a circle are congruent. Now, if I name each of the angles, notice the two angles in the left triangle are congruent. The two angles in the right-hand triangle will also be congruent, but not necessarily to the ones in the left-hand triangle. Then I have a triangle that has two B's in it, which means the angle at the vertex of that isosceles triangle is 180 minus 2B. On the right-hand side, I have a triangle with two angles with measure C, so its vertex angle is 180 minus 2C. Now, by definition, I know that the measure of an inscribed angle, the measure of a central angle is equal to the measure of its arc. So the measure at the center up here is 2A. Now, I know that the angles in a circle add to 360, so I can set up an equation and figure out what's going on here. So let's start. I had 180 minus 2B plus 180 minus 2C plus 2A equals 360. Combine my like terms and then subtract 360 on both sides, and I had 2A minus 2B minus 2C equals 0. I was trying to find out something about the inscribed angle, but I wanted its relationship to the arc up here above it, which was 2A. So I solved the equation for 2A, divided both sides by 2, and figured out that A equaled B plus C. Now, I can tell that B plus C together is my inscribed angle, so that means the measure of my inscribed angle is A. What this does is it makes it easy to find measurements. If the arc had been 100, the angle would have been 50. If the angle had been 20, the arc would have been 40. Let's go ahead and look at an example using that. We have an example with lots of wonderful arcs on it. The first thing we should do is go in and mark the information we know. We know that arc WX is 20 degrees, arc XY is 40 degrees, arc UZ, that's all the way it passes through T, is 108 degrees, and we know that the other two arcs are congruent to each other. Don't know what they are, so I'll call each of them X. Now I know that all the arcs around the circle add up to 360, so 20 plus 40 plus 108 plus 2 X's equals 360. 168 plus 2x equals 360. So 2x subtracting 168 gives us 192, and x equals 96 degrees. So now I know what almost all of the arcs are on this circle, but I have enough to be able to tell what I'm working with. First, let's look at angle 1. Angle 1 is down here. The arc inside angle 1 is arc UW. So I know the measure of angle 1 is going to equal 1/2 of the measure of arc UW. So that's 1/2 of 96, which is 48 degrees. Moving on to angle 2, I look and see what arc it intercepts. And I can see angle 2 intercepts arc XY, which is 48 degrees. So the measure of angle 2 equals 1/2 times the measure of arc XY, which equals 1/2 of, not 48 degrees, I can't read my own handwriting, 40 degrees. And half of 40 is 20 degrees. Let me make that look better. There we go. The next angle is angle 3. And as I'm looking at angle 3, the arc that angle 3 intercepts has already been done in red, and that's arc UZ. So I know the measure of angle 3 equals 1/2 the measure of arc UZ, which is 1/2 of 108 degrees, which is 54 degrees. And then I looked at angle 4 and said, uh-oh, angle 4 is not a central angle. Angle 4 is not an inscribed angle. I don't really know how to find it yet. Let's go on to angle 5 and then go back. So I looked at angle 5, and the one thing I noticed is that angle 5 actually intercepted the same arc as angle 3. Well, if they intercept the same arc, we're going to take half of the same number, and that means that the measure of angle 5 was also 54 degrees. This is actually the next theorem. If two inscribed angles of a circle or a congruent circle intercept congruent arcs or the same arc, then the angles are congruent. So this hopefully should make sense when we look at that. Now let's go back to poor old angle 4 here. We'll learn a different way to find this in the future, but for right now, I know that angle 4 is part of a triangle. It's part of a triangle that has angle 2 and angle 3 in it. And I know that the angles in a triangle add up to 180. So, to find angle 4, if I take the measure of angle 2 plus the measure of angle 3 plus the measure of angle 4, it should all add up to 180 degrees. So let's go with that. The measure of angle 2 was 20 degrees. The measure of angle 3 was 54 degrees. Plus the measure of angle 4 had to equal 180 degrees. So 74 plus the measure of angle 4 equaled 180 degrees. Subtracting 74, I get the measure of angle 4 equals 106 degrees. So using old information, I was able to go ahead and figure that out. Now let's take a look at the next couple of theorems. One of them says if two inscribed angles of a circle or congruent circle, so you can move between circles as long as the circles are congruent, intercept congruent arcs or the same arc, then the angles are congruent. Now, think about that. If they are intercepting congruent arcs, you're taking half of the same number no matter what. Now, if you look at these two angles I've just drawn, this is angle 1 and angle 2 here. They both intercept, let's call it arc AB. That means angle 1 equals half of AB and angle 2 also equals half of AB. Angle 1 is going to have to equal angle 2. Now, if you put an angle in a congruent circle and you know that arc CD over here is congruent to arc AB, so if this is 100 degrees and this is 100 degrees, when you're looking for the angle, you're still looking for half of 100. That means those angles are all going to have to be congruent. So angle 1 would have been 50, angle 2 would have been 50, and angle 3 would have been 50 degrees. That explains that theorem. Now let's take a look at the next one. If an inscribed angle intercepts a semicircle, which means we need a diameter to get a semicircle, then the angle is a right angle. This is kind of a cool way to draw right angles, by the way. If you have a circle and a diameter, all you have to do is connect that to any point on the circle. Now think about this. This is going to be 90 degrees because the intercepted arc is the semicircle, which is 180 degrees. Definition of the measure of an inscribed angle is half the arc. That means the angle over there had to be 90 degrees. It doesn't matter where I put that angle on the circle, it's still hitting that 180 degree arc. And so we end up with the 90 degree angles. Looks a lot like a spirograph drawing going there. Now, let's take a look at our next theorem. This one's a little bit trickier. It says, if a quadrilateral is inscribed in a circle, then the opposite angles are supplementary. So let's just name two of the angles in here. I'm going to name this one 1, and I'm going to name the opposite angle 2. And if I color the arc that angle 1 intercepts, it takes up that portion of the circle. I don't know how much of the circle it is, but it's part of 360 degrees. If I look at angle 2, the arc inside that is the remainder of the circle. So basically what I have here is that if I add the red arc and the blue arc, I know that together they are the entire circle. Well, I know that the red angle, angle 2, is half of the red arc. I know that the blue angle, angle 1, is half of the blue arc. So if I put the two angles together, that's going to be half of 360. So half of my first arc, half of my red arc, plus half of my blue arc is going to have to equal half of 360. Well, half of the red arc is angle 2. So I know the measure of angle 1, 2. I'm having a little issue here. Plus the measure of angle 1 together are going to have to equal half of 360, which is 180 degrees. I know that any two angles that add to 180 are supplementary angles. So I've demonstrated that theorem. Now let's do our last two practice problems. First, let's look at what we know. We know that VU and SU are congruent, which means that angle 1 and angle 2 are congruent. We know that UT is a diameter, which means the angle at S and the angle at V are both 90 degrees. And I know that I have two right triangles here then. And when I look at a right triangle, I know I already have 90 degrees here, which means out of my 180, I have 90 degrees left for the remaining two angles. So I know that the measure of angle 2 plus the measure of angle 4 equals 90, or x plus 9 plus 2x plus 6 equals 90. That gives me 3x plus 15 equals 90, or 3x equals 75, and x equals 25. Using that, I can now figure out what each of these angles are. I know that the measure of angle 2 equals 25 plus 9, or 34 degrees. So I know angle 2 here is 34 degrees. That means angle 1 is also 34 degrees. I know the angles in a triangle add to 180. Or I could substitute into angle 4, and 2 times 25 plus 6 is 56 degrees for angle 4. And by the same token, I can say that angle 3 is also 56 degrees. We have one more example. I'd like you to try it on your own and then check your solution. Be sure to draw a diagram. Check your answers. We use the last theorem. This concludes today's podcast.